programmable systems or chip course. This is very much hands-on course, since basically you cannot learn this kind of very applied stuff without applying it. So we will be playing a lot with these design kits. Oh, wow. Okay, there are already some parts there. Oh, good morning. Good morning. First things first. So that is the website. Probably you have already found it. It's based on Google site, so I would guess that if you Google this course, you can find it that way too. With a mobile phone, you can just click that QR code there. Okay, that's my name here, Antti Piironen. If you want to send me email, it's antti.piironen@metropolia.fi. Very simple email address. Okay, good. Let's go a little bit forward. So first things first, enrollment. So if you haven't enrolled to the course yet, there's an enrollment link right there. I have something like 11 different names on the enrollment list. So click that one, then you agree to give your index finger for me and your soul for later use. Not really. When you are, I'm asking some personal items, which are basically also basically secured by that's GDPR Act of EU. So I'm not using that information anywhere else except giving you grades. I cannot give you grades unless I have the full name and your birthday. Okay, those are the must places, and actually all the must items you need to fill. But anyways, you can, if you are not okay with that, then you can always come with the paper clip and give it to me. I will use it afterwards, just give you some grades. Okay, so enrollment. Classes from today to Friday. We start every day at 10 o'clock and then we end around 4-ish. Meaning basically that I usually, after 2 hours, you are tired of hearing me anymore, and I will then let you work a little bit, some exercise. Okay, so hardware. You need some specific hardware. Some of that part is here already. Some of those kits you need to go and ask Robert Mikalik. We will have sometime we have a break after the that mandatory theory part. We will have a break to get these kits. Oh right, so either Robert Mikalik or Mr. Umansky will have their here. You know those guys, yeah, right, definitely. Okay. Those are the topics. Today we go through the fundamentals. So just get some practice on the development tools, how to use them. And tomorrow actually we will have the timers and PWM stuff. We will have some servos, I hope there. Yes, we do. Some servos. So basically we'll practice using these PSOC circuits to do some timing and PWM. On Wednesday, A to D conversion and sampling. Okay, so yeah, those things. On Thursday, serial interfaces, how to get the data out of the system, for example, to your computer. And then on Friday, we have more serial interfaces, especially these chip-to-chip serial interfaces like SPI or I2C. Actually, on Thursday, we already have the one wire. And that will be the Friday part, and the rest of the courses, this is 5 credits. You cannot do 5 credits in 1 week. It's, impossible. So that's why we have also a project to see if you learned something. Project topics, actually, you can also suggest your own topic if you have some specific need. So this is quite powerful microcontroller what we are having here. It's not just the microcontroller. It also includes all sorts of peripherals inside of it, programmable peripherals. All right, so, and the scoreboard says online scoreboard is not currently available. That's I need to now ask you if it's okay to publish the scoreboard on internet using your first names only. I'm not putting your last names there, just first names. Is that okay for everyone? Okay, no objections. Nobody's objecting. Good. Done. And that's actually, I have the record of that one now. So yeah, I can actually, let's see, I think I can already. There we go. I already have this scoreboard there. So that's what the scoreboard looks like right now. If your first name is not here, then it means that you haven't enrolled yet. Okay, so go and click on the enrollment link. All right. There we go. So let's take a look at the first topic. Any questions this far? So practically, every day we have a different topic. I speak a little bit, show you some hints, and then after that you will start working on either alone or in pairs, or well, maximum 3 students in a group. If there are 4, then it's better to split that in 2 groups or 2 pairs. Okay, and the deadline, the absolute deadline for the first exercise is on Friday before I leave. So I try to make sure that everyone knows how to return the exercise. All right. So the first part is fundamentals. And as you can see, there is actually my last year presentation right here, the same stuff or quite similar stuff. The change for this year is basically that I have also given opportunity for students to learn PSOC 5 in addition to PSOC 1. PSOC 1, the main differences between PSOC 1 and 5 is that PSOC 1 is the original first version, which has just 8-bit RISC processor, but it also have huge amount of software configurable hardware. So if we take a look at this link redirecting, there we go. So that's the PSOC 1 architecture right there. So we can see that it has a lot of stuff there. It has a 8-bit microcontroller core. Is there a no pointers? Okay, I will just show you with the mouse. I hate the mouse though. Okay, so it has a processor core as usual with some static RAM and flash program memory, and then the ordinary stuff. Okay, some extraordinary stuff. It also have the multiply accumulate, the special register, meaning that it can do also some, say, digital signal processing faster than any similar processor without the MAC unit. Then it also have these Other hardware stuff like I2C, well, any processor have I2C. Decimators, well, that's part of the making the digital signal processing going faster. It has watchdog sleep timer. Yep, sure. Which processor doesn't have? Still the same. And low voltage detector. Yeah, most of the microcontrollers designed for low or battery power actually have this one. Then of course interrupt controller. What makes it special is those green areas here. It has digital block array. So fundamentally it has a small block as a similar to those programmable logic devices. This is software programmable block, register driven block, which means that you do not need to use software, for example, telecommunication. You can directly use hardware for that one. And this one gives also a very flexible way of doing the different hardware functions. So it means that we are not straining that small 8-bit processor for calculating too much of, say, routine kind of things that can be directly programmed to this digital block. And then what makes it even, well, the digital block arrays you can find from, I think, Texas Instruments circuits too, which is really unique for Cypress PSOC is that there are also this analog block array, both continuous time and switch capacitor type blocks, meaning you have programmable amplifiers, programmable multiplexers, programmable filters, analog filters, and of course a different type of A to D converters and D to A converter possibilities in the same chip. Okay. And then it also have this configurable I/O port, quite nice big way. You can actually select almost any signal to digital signal to any output or input. Analog signals, I think they were just for port 0 and a couple of extra pins. But anyways, it's a kind of really nice flexible system, which means that it's not that straightforward to program anymore. Everything is driven by software. And what happens there, of course, you need to write the code that makes the configuration correct. But that's why we have we have these nice design tools. Okay, so that's the PSOC 1. 8-bit processor. PSOC 5 is what? Let's see, which one was that? 54. Let's take that one. Does it have the similar? Let's see some of these. PSOC product portfolio roadmap. Okay, that basically says almost everything what you need to know about this. So the original PSOC 1 is right here on the left corner. Okay, and then there's also 8-bit processor PSOC 3, which has the 8051 core. It's not dead yet. It'll never be. Okay, and these are still 8-bit processor, but they are actually okay. 32-bit ARM processors in PSOC 4, 5, and beyond. So basically, I kind of sort of like the PSOC 5 because, well, I didn't know the PSOC 6 to come. Actually, it was launched, I think it was last year on December or something like that. New stuff. But anyways, that latest PSOC 6 is quite nice since it has the Cortex M4 or M33 depending on the device, which means that it really runs well with the digital signal processing. It has the real floating point unit already in there, and it makes a huge difference when you are doing, say, digital filtering of any kind. Okay, but anyways, so we are using PSOC 1, or if you want to learn yourself PSOC 5, it's not that much different. I can give you a short introduction on the tool chain. It's different. It has less capabilities on the hardware side, but on the other hand, the software side, well, it's ARM processor. You can do anything what you basically can imagine with that thing. And it also has some of these the programmable type devices inside. Okay, let's see. So PSOC 1 or PSOC 5. I recommend you to take the PSOC 1, and basically after you have done these 5 exercises with PSOC 1, one possibility to make the project is to do the same exercises with PSOC 5. That's one possibility if you want to learn also that environment. All right. Yeah. Each of these topics I also have these exercises. So exercise 1, for example, on PSOC 1 exercise or PSOC 5 exercise, they're a little bit different. Actually, they go a little bit more different on the last exercises because of the different capabilities. All right, let's take a quick look at exercise 1, fundamentals. Yeah. So if you have of course you have the Google account, right? Gmail account. Everyone has Google account. Is there anyone who does not have Google account? You don't have a Google account yet. Okay. Which cloud service are you using for files? Okay, it works. Yeah, it works. But anyways, I use Google just because it's free forever, hopefully. Easy enough. There are not too many gadgets there. It's just, very compact thing. It works well for my purposes. But of course, there are also other cloud service providers. And Google is not paying me, so I'm not forcing you to use it. But anyways, whatever I have material on my internet, they are basically governed by the Creative Commons, share alike, non-commercial use. So if you find some use for any material there, feel free. You can redistribute as long as you don't change my name to your own name. All right, but anyways, so some exercises what we are doing today. Actually, we could start doing the first exercise without those hardware. And then we'll go on the next break, we will go and check the hardware. But just to get acquainted with the system design tools. Okay. Do you have your own laptops? Probably. I actually recommend you to use your own laptops because, well, then you can also practice it on your own time or go to Mensa and have a cup of coffee and spill it over the hardware. Yes. Oh no! Oh no! You don't have oh, okay. Well, maybe you should team up with somebody else for today, and I would guess that the design tools are also on these computers. If not, I think you can actually install the designer. Anyways, how to start everything? Hmm. Let's go back to uh, this page, PSOC 1 page. You need to download the PSOC designer, which I think you also need to register to Cypress. They want your finger and your soul, part of your soul. All right, but download the PSOC designer. It's free tool, and by the way, these chips are not that expensive either. So, for example, this PSOC 5 design kit. And this is ARM Cortex C3. It's about €10. Okay, it's nothing. Practically, this is almost free of charge, but if you want to buy some of those, you need to discuss with Robert Mikalik. Okay, so download PSOC designer. Actually, you are also lucky you are students in University of Applied Sciences. There's also you can have a sample request. You just need to register yourself as an academic user, meaning student user, and the Cypress is very good on donating kits to students, since you will be the future engineers and they want future engineers to buy their stuff. And chips are very cheap. Okay, but anyways, you need the PSOC designer. There we go. And on PSOC designer, let me. Okay, maybe I should. You will get this kind of icon on your workspace. PSOC Designer 5.4, and clicking it will open the designer, hopefully. But of course, it takes for a while before it's uploaded. It looks like that. So did you get your PSOC designer to download? Is it downloading it now? Is the PSOC designer already installed on these computers? It's there. Okay, excellent. You don't need to register later. So the basic designer seems to be on these computers if you want to use them. So does everyone has basic designer on hand for right now? Maybe should I wait for a couple of minutes and take a quick look? You have one version of it, right? There's also one version. You have basic designers. So yeah. So basic designer, right? That one. Okay, good. So everyone has a piece of design. Just still downloading. Could you team up with somebody else? So let it download. It takes for a while. You probably get if you are not registered yet to the Cypress systems, then basically it asks you to register now. But you can actually on these fixed computers just click register later. But register basically means also that you get the latest upgrades for automatically. So, and that's part of the giving your soul to Cypress. All right, but that looks empty right now. We will be using. Okay. Where's my mouse? All right. So how to basically proceed here? Starting up piece of designer, then starting a new project from scratch. Alrighty then, let's start from scratch. How to do it? We can click here, new project. Click. Okay. Give it a good name. Well, PD project 1, that's just fine. Documents, that's not okay for me. I'll just, that was something else. PSOC 4, 5.4 designer projects. That's, I think that is a good place to put this one, for example. One idea is actually to add your name on the project at some point. So, for example, like this PD project 1, and then your first name or something like that. Next step, you need to make sure that, since this is the place where you fix the processor, there are plenty of variability here. For example, if you take a look at the device catalog here. Okay, does it open? Yes. Device catalog has something like way too many processors to click. So you need to actually find a processor that fits into your needs. One way of doing it basically is to just set the pin count and package type. Let's see. So parallel dual inline package. Okay, that's much better now. Pin counts, well, then we could actually also, if you know how many analog blocks you would need or digital blocks, you could use those as parameters. It also, some of these chips actually have the direct capacitive sensing capabilities. We don't need that. What we actually need is type. Okay, let's see, what was the type? CY8C27443. There we go. That one. And it says 28-pin parallel dual package, 12 analog blocks, and 8 digital blocks. It has 16 kilobytes of flash and 256 bytes of RAM. Yes. 443. 443. Yeah. Find it? It actually also states that one in the exercise sheet. Yeah, 27443 there. Uh, 27443 24PXI. Yeah. Yeah. Okay, 24. It's also on the exercise sheet. Okay. Next time you go into this program, actually it remembers your last choice. There, click that one and create project with this processor. You can also find an example project. There's tons of different examples already done. Similar way that Arduino, the only difference is that these Cypress projects usually work. So, are you familiar with Arduino processors? They're used everywhere, but those are toys. They are not used in any automotive applications. Cypress processors are. Cypress processors are also used as a co-processor in lots of handheld devices, since they have pretty good capacitive sensing properties. Okay. So, generate main file using C. You can also try your luck with the assembly code, but, well, this is not IKEA. This one does not need assembly that much. Okay. There we go. And now it creates the project, and we have a kind of funny place to start software design. The software design actually starts with the hardware. They are on the top, there are those 8 digital blocks with the row and row lines, and then these column lines for routing the signal. It also have the mark the inputs and outputs. Then on the bottom we have the now this is go. There. On the bottom we have this analog 12 analog blocks arranged in say in three block columns. Okay, so how to start programming this? Well, we will start actually by adding some pre-made the user modules. On the right low corner, there are these user modules that are available for this processor. And you can find there A to D converters, about 10 different types. Amplifiers. So these are basically analog amplifiers inside of the this system. So you can, okay, let's go down here. You can actually select these functions to these analog blocks. Analog communication, okay, well, only one. That's a dual tone, multiple frequency dialer already there. That's a block. Counters, 8 to 32-bit counter available. D2A, different kind of D2A devices. Then digital communication, different blocks for example, I2C, infrared data, one wire, SPI, both master and slave, and SM bus slave. It has UART, full UART, then it has a transmit and receive 8-bit thing. So okay, you can do a lot with those. Practically, you can connect almost any digital sensor to this device, or practically all the digital sensors, without need to write extensive amount of code, since the code comes with the module. The application programming interface comes with the modules. Okay, then we also have the analog filters, switch capacitor type of analog filters. Some nice generic stuff, LED dimming kind of thing. Okay, legacy means that old stuff which still can be used. This is probably the most used set of tools. There are the miscellaneous digital. You have, well, since you have this flash memory there, you can actually define part of that as non-volatile data memory, as EEPROM. Okay, it has software drivers for LCD or 7-segment LED device, and sleep timers, that kind of stuff. Analog multiplexers, good. Some power management protocols. Okay, protocols. Well, you can also have external I2C memory to use that, and use that one as the program memory, and have a bootloader that first loads the boot code from the I2C chip and then starts executing it. Well, different pulse width modulations, random sequences. So if you need random numbers, you can do it hard way. That's the hard way, which is the easy way. Okay. Yeah, temperature, thermal management, and timers. So okay, so basically this temperature is the internal temperature of this chip, like the flash temperature. You don't want to brown out the flash. Okay, and in addition to that, you can start building your own custom modules. Okay, so all of those are available within the available resources, of course. This chip has only 8 digital blocks and 12 analog blocks. But basically, we can also make different loadable configurations, meaning that if you have different operating modes needed for that processor, you can make it basically double or triple or quadruple to the number of usable blocks by just simply making another profile for the operation. So loadable configurations. But usually, well, this course actually we have only one loadable configuration. The loadable configurations are pretty handy when you need to put the device in a really deep sleep mode, meaning that it doesn't consume much of energy then, only a couple of microamps. Then you might have a more complex design. One, the operating mode, and the sleep mode, you just have another the almost empty design there, which just have the sleep timer and wakes up once in a while to check if there is need to turn it on the operating mode. That's how my electric fishing lure works. Yeah. Alrighty. So, some blocks. Let's add a couple of blocks. Let me take a quick look on adding modules. Datasheet. Okay. How about adding just a simple block called LCD? Something that worries me always is how to find my bug. Since when you are starting to write your code, you need to have first some debugging method. You need any debugging method. This PSOC 1, or actually all the PSOCs, come with the LCD driver, meaning that a software package to handle a standard LCD. And as you can see, it did not actually do anything for the hardware yet. The parameter on the left middle box. Let's rename the parameter, rename this block as LCD. Then select the port. There are 3 ports available. On the design kit, this LCD is actually on port 2. Something happened. It actually now renamed this port 2.0 to 2.6 and reserved those to LCD. There's still 2.7 is still usable. You can use it somewhere else. Okay, and well, depending if you want to also use some bar graphics there, then it either enable or disable. Usually I disable, since, well, for debugging I don't know if I need any bar graphs there. Okay, next step. Well, actually this could be the first step also. Let's take a look at the datasheet. What is this block all about? Yes, there we go. A little bit. All right. All of the blocks what were other on the right low corner of this designer actually have the data sheet. Pretty good one. So first there's a table of the resources what it needs. Okay, this is a software block, meaning that it just takes some pins and then it's the application programming interface takes some flash bytes. Some of these blocks actually also reserve static RAM. Then it cannot be used by any other. Okay, features uses the industry standard Hitachi HD 44780 LCD display driver chip protocols. Practically 99% of the LCD displays follow that protocol. Okay, and if you want to make your own circuit design, it also gives you the pins where they should be actually going. So after selecting the port, you need to do the wiring. On those design kits, we have the pre-wired port to the LCD port. Okay, good. Other stuff, functional description, excellent. Yeah, sure, why not? Placement. Placement means that where if this one requires hardware, how the hardware is allocated. And this one actually just takes those pins, but no digital blocks. Then the most important part is the application programming interface. It tells you which functions you can use. That's nice. There's a C prototype for the function and how to use it. So practically you just call the LCD start without any parameter, then basically it starts the device. Okay. Just like car, you need to first start the car before you can start driving it, right? Okay, LCD init, initialization routine, start is actually enough. Yep, it actually says the LCD start function should be used instead. Remember, there are something like more than 15 years of history for the tool set, so there are some functions still available which are replaced by some other function. Then let's see what else. Position, LCD position. You can pinpoint the cursor position on the LCD. Print string. If the string is a variable in RAM, then you use this one. But if the string is constant, meaning in flash, then you need to use another function. That's the most confusing part of the using these functions. How to basically make difference between the constant strings and the these kind of soft strings. So if you set a variable on the variable definitions and set a value for that variable, then it's a normal variable string. If you place that string inside of, for example, on a function call, or define a constant string somewhere and use that one, then it's actually on the code. It goes into code memory. Okay, so now this one actually brings some more details about how C programming language works. So when you have the main routine, usually the variables are there. If you have a variable, for some character variable str with the size of, say, 8 byte, and then let's see, how does it go, equal to, say, test, something like that, then this is definitely a variable, nothing else. If you mark here const, then it's constant variable, meaning it's ROM. Okay. If you mark here static, it's still on RAM. Okay. So, and if you have, so basically this part is constant. But if you put it like this, then it basically allocates this memory and the initializes the value of this string with that constant. So that's the difference between constant string and normal variable string. All right. Okay, then LCDPR hex byte, meaning that it prints a hex byte. Very useful for your debugging purposes. You don't need to turn into, the 10 base integers. You are engineers, you can read hexadecimal. All right, and yeah, 8-bit integer is byte, and in this environment, the integer has 16 bits. That's one of the funny things about C programming language. The character is 8-bit integer, but what is the length of integer depends on the device and this programming environment. That's why there are also these extensions like int16, int32, and that kind of things, which are not part of the standard. But most of the compilers use those. So int in this system is signed 16-bit, long integer is signed 32-bit. Okay, but anyways, print hex int means that it would print a 4-character hex string, hexadecimals. Then bar graphs, yep, that kind of stuff, and so on. Optional functions, control, write data, okay. So if you need to write some special code for example, finding special character sets from that the LCD controller, you need to then basically write the control code and find the character set, change the character set, and then you can write whatever. Okay, and some others. All of these, the data sheets, they come with examples, both in assembly and in C. That's nice, since now we have on our design, we have, let's see, on design we have just the LCD module. Where's the LCD module? There. On port 2, and here we have a sample code. Interesting. Let's copy that one. And do some magic here. Let's click on this small icon here, which cannot be seen. Okay, it's just under the build. There's a small icon which has 3 boxes. And when you move your cursor over it, says generate configuration files. You can actually do the same thing on the under build, I think. Generate here, generate configuration files. This click actually now goes and checks what modules you have on your design, and it gives you the subroutines from all the required files, all the required files for the project. So pre-written code based on what your configuration is. Nice. So, for example, here the library source files, of course, those are assembly files. They are these since that's the best ways to ensure that the code is optimized. There are also library header files, both for C programming and assembly programming, but let's take a look at those later. But what it actually did, that generate header files, generate configuration files, it gave you two codes here. boot.asm. You don't want to touch that, it's ugly. It's assembly code. But of course, that is the code that starts the program. That's the boot code, which has initialization for all of those routines what you add, or initializations for everything what you did on this designer part, and then it calls main function. Okay, again, main routine in C language is still a function. It's just the main function, just like any other function. There must be some code that calls that function. Okay, so let's double click on the boot.c and see. Okay, looks like we have some code here, but I have better code on my buffer. That's a fast way of coding stuff and testing if a example code actually works. There are actually some errors on the code given, and this is not complete. This is absolutely not complete stuff here. We'll fix it. But anyways, that's basically what I'm expecting all the code to look like when I'm getting the returns. On the top, there's supposed to be a section for comments, what this main function actually does. Then next part is what include files it needs. Then it has the main file prototype, or main file right here, or main function. One variable defined, and that's a RAM string. Yes. Oh, okay. You can leave that one actually open. So basically, now this is a standard variable definition here, and simple program just start the LCD, puts the position on the first row, 6th element. So this is from 0 index. Indexes start from 0. And then it has just the string, and then what else? What is missing? You have been doing some microprocessor coding before. What is missing from this one? Yes. I call it operating system. Yes, so this is microcode, so basically it should have the loop forever at some point, since you don't want to exit this main function without knowing where it exits, because it's such a function. After that last line, it goes somewhere. Okay. There might be actually a that one loop on boot.asm, but no guarantees of that. I'm not touching it. Okay, so basically this is all code needed to print some characters on the LCD display. And now I have been basically talking about 1 hour already. without a break. So now we have a short break and line up to Robert Mikael. Hope he's there, and borrow the those Cypress piece of kits. I need one too, so I will be on the first on the line. Okay, but anyways, let's have a small break right now.